Da, bine.
Say welcome back. Last couple days we've learned about white dwarfs and we've learned about different star systems, and today we're going to be going down the black holes. So welcome back, and welcome to everybody who's watching live on Facebook. And I'm going to give the mic over to you, our expert, and thank you so much for being with us today.
Okay, thank you for inviting me. So this is the third lecture in the series on physics of compact stars. And we did the first time white dwarfs. Then yesterday we did the neutron stars. And today we are going to talk about black holes. So let me share the screen with you. As I told you yesterday, because you have to enable me the screen sharing, Alex. As I told you yesterday, because my computer may crash, which actually happened yesterday, I have now a second computer already prepared. So if there is a crash, no problem, I have the PDF on the other computer, and then we continue there. Okay, I was just curious, I didn't solve yet. So indeed, the chat window disappeared once I shared the screen. So what I have here on this on the screen is a very nice, actually, illustration of a black hole, which looks like the one in the Interstellar movie. I don't know if it is precisely from the Interstellar movie, but this image became an iconic image, and it's really, really, really nice. So what you see here on the right is the black hole. Let me make the pointer here. The black hole, and they have an accretion disk around the black hole, and you also see some planets here floating around the black hole, and this is actually the story from the Interstellar. Again, as I told you yesterday, something about me. You may find me on YouTube, but as well on Discord. We have a lot of discussions on Discord. Every Wednesday and Thursday, we have somebody, and actually after this meeting, I'll go to Discord because we also have a guy who does YouTube, and he's going to be our guest this evening. And you can buy my book or find me on YouTube. This is the, let's say, the drawing which is in my second book and which I showed you already twice. But this basically tells the story, and I think I have a crash. Can you confirm, Alex, that you don't see me moving?
Yeah, your screen has frozen again. So let's see. We can get that back. I think he'll have to chime in again with the link. Alex, are you there?
Yes.
Okay, great. I think the same thing from yesterday. I think he's going to just hook in with the other computer and connect that way. So hopefully we'll see him soon.
So I think you see me now with the other computer.
Yes, I can see you now, and I still see the screen on the other
Yeah,
one.
so I will take the electricity out of the other computer.
Okay, sounds great. Yeah, your picture's perfect.
So this should solve the problem. Otherwise, it's from Alex.
No, actually, your picture's perfect. It looks great. So we'll reshare your screen.
Okay. This is stop. Do you want to continue? Yes. Share. Can you hear me?
I can hear you.
So you cannot hear me. One moment.
I can hear you. I can hear you, yes.
One moment.
There we go.
Okay, I can hear you. Can you hear me?
Yes,
it's perfect.
Oh, okay. It's not yet perfect on this one. Here says low system resources.
Oh, is that a battery?
No. Battery is okay.
Okay, good.
Cancel. But the point is, do you see me or do you see my screen? Ah, you see me.
I see your screen. I
okay.
see your Zoom screen.
Okay.
Now we see your presentation. The black hole is there.
Okay, that's good. We start with the black hole.
Back in business.
Yeah, exactly.
Back to the black hole.
So this should be a PDF presentation. Yes. So no more videos, unfortunately. So I just choose PDF now on this laptop to be sure. We discussed last time about how these compact stellar objects are created. And we saw that everything starts with a nebulae when there is a lot of hydrogen. And then you form a star. If the star is small, so in the top part, then the star is going, at the end of the lifetime, is going to become a red giant. And then the red giant is going to shed out the outer layers. And what is left over is a white dwarf. If, however, the star which is formed has a mass larger than 8 solar masses, is going to form at the end of lifetime a super red giant, and that is going to explode like a supernova. And depending on the initial mass, if the mass of the star is between 8 and I don't remember precisely if it is 12, something like this, at the end, the remnant is the core remnant, which has a mass of about 2 solar masses, becomes a neutron star. But however, if the initial mass is larger than 12 solar masses, then you have a remnant which has a mass, the core mass, which may be larger than 3 solar masses. And then what is inside is a black hole. This is the supernovae explosion. So the point is, and I will stop sharing the screen so that you can see me. So now you see me, yes? Yeah. The point is the following, that what is important is what is in the core of the star. So you have the explosion of the supernovae, which I described last time. So the many things go away, the outer layers, a lot of things from the star go away. So even though the star may have, let's say, a mass of 15 solar masses, most of the materials, most of the atoms go away. And what is left over is the core. But the core suffers some processes. So in the first instance, the core becomes a white dwarf. So in other words, it fuses carbon. But then the pressure is very, very high because of the gravity. So in the core, you start fuse also to fuse other elements. And then you get all kinds of elements, oxygen, carbon, and so on and so forth, until you get to the iron. And then when you get to the iron, then the supernovae explosion, because the iron cannot burn. But then the iron itself starts to collapse because the core itself has a very high mass, and because of the gravity, the iron itself collapses. And then you get a neutron star. So you have neutrons, so all the electrons which are there inside the iron combine with the protons, and they form neutrons. And then there is a neutron star. And when you have a neutron star,
you have the degeneracy pressure of the neutrons, which try to keep the gravity. But remember, now the mass of the core is even larger than it was when there was a neutron star. And because of that, this degeneracy pressure of the neutrons cannot support gravity anymore. So then the neutrons collapse as well. So in other words, you break up the neutrons in whatever they are, and everything starts to collapse towards the center. And that's the moment when you form a black hole, because there is nothing which can prevent the gravity, you know, pushing it to the center. You wanted to say something, Heather?
No, it was a wonderful review of the last couple days of how we get to this point of a star becoming a black hole. So
Yeah.
thank you for just going over that again for me and for everyone listening.
Yeah. So then indeed everything collapses into the core, and then they form a black hole, in the sense that everything goes towards the center of the core. So that's actually the most important point. Let me see here, because I want to share again the screen. More. I have to find out, share the screen. I find the button here. Okay, so now you see again my screen, full screen. And the real point is, okay, what is it going to happen? Because if you have the neutrons and they cannot hold anymore because there is a lot of pressure, and the core collapses towards the center, what is it going to happen? What are you going to have then? Well, the point is, you are going to have in the very, very center what is called a singularity. So in other words, everything collapses in a point which is so small that, you know, it's smaller than the point of a needle. It's smaller than the point of the needle. Even if there's, you know, so many solar masses, that point itself is smaller than the point of the needle, or it's even smaller. Actually, nobody knows how small it is, but everything collapses in that point. And that is what we call basically a black hole. A black hole is a region of empty space, and that's what I try to draw here. It's really empty space, which has in the center of singularity, where everything collapsed. But otherwise, it's empty space. And I draw here a sphere around that point, the singularity, and the sphere is called the horizon, and this is an imaginary sphere. And people refer to that as the border, or as the margin or the border of the black hole. But it's not something that you have to see as, you know, hard border. It's like there is somebody there checking your passport. There is nothing there. This is an imaginary border. But we draw this imaginary border around the black hole because that's the point of no return. That means if you come across this border inside the black hole, then you cannot escape. So the black hole is everything what is inside this imaginary border, and we know that once you cross the border inside, then you cannot escape. But otherwise, it's empty space. So what is the black hole? Well, a black hole is an imaginary sphere of empty space with a singularity at the center. And in that singularity, you have the mass of, you know, in this particular case, of 4 or 5 suns put in that very, very, very small point, smaller than the top of the needle. And actually that kind of black hole was kind of predicted in the year 1783 by John Mitchell, who said, well, imagine what would happen when you have a star which is more compact and more compact and more compact. As we saw last time, if the star is smaller and smaller and smaller, then the gravity at the surface is stronger. So you feel the force. If you sit on that star, which is very, very small, like a neutron star, you know, you feel the gravity. It's very, very strong. So it's very hard to actually jump on it. It's very, very hard to jump on it. And the smaller the star, the harder it becomes to jump. And the physicists quantify this with a term which is called escape velocity. So in other words, if you are on a smaller planet and you want to send rockets outside, yes, you have to send the rockets with a certain velocity. So I will again stop here. So if you are on that star which is small and you want to jump on it, the smaller the star, the more difficult to jump is. And then if you want to throw away something to escape from the gravity, you have to throw it even faster, you know, and the smaller the star. And John Mitchell said, wait a minute, if I have a star which is like sun, and I take all the mass and put it in a sphere with a radius about of a radius of a city. So in this particular case, I think the radius is 6 kilometers. So if you have all the sun squeezed in a sphere of a radius of 6 kilometers, I think more or less, then the escape velocity is so high that is higher than the speed of light. In other words, if you want to send light outside, even light cannot escape because it doesn't have sufficient velocity. So that's why he said there must be in the universe some stars which are black. So he called that black stars because the light cannot expect. And today we call them black holes, but we know that they have very, very different properties. And in particular, again, black hole is not a star, it's not something with material. Black hole is empty space. It's just empty space with a singularity at the center. And the radius, for the radius of a black hole, we use more or less the same formula which John Mitchell said. And for the sun, the radius is about 6 kilometers. And it's called Schwarzschild radius. And now, of course, let me see. Schwarzschild was a German in the First World War, and it has a kind of nice story, but also sad story, because after Einstein published his equations, Schwarzschild took the equation and said, well, what is going to happen if I have a small star with a lot of matter, very dense star? And he knew that that is very important for Einstein equation, and Einstein knew as well, because what does Einstein says? He says the following, as we saw it last time in the previous episode. If you have mass deforms the space around, and the more compact the mass is, the larger the deformation. And Schwarzschild took his equation and he calculated, wait a minute, but if I have a star which is so small, like Mitchell said, how much, or larger, or the sun and so on and so forth, how is the space going to be curved around the star? And he found out the solution, and the solution looks like this very famous here picture, which I show it here on the right hand side. Now, what do you have here? Every time you see this picture, you have to remember this picture represents the space around the black hole, but in the equator of the black hole. In the equator of the black hole. That means you stay always in the equator of the black hole. And let's suppose that you want to enter on one side and you want to exit on the other side. What this surface tells you is that normally it would be very quick to go from one side to another. But because the space is deformed, you have to enter this hole here and exit. So the formula tells you actually that there is a lot of space inside the black hole. And I don't think that Schwarzschild, certainly he didn't calculate it for black hole, he calculated for the sun or for the other objects, but this formula tells you that you generate more space, that the space becomes larger. And just to give you an example, so if you look at me, I try to imagine the following. How is it that you have more space there? Well, imagine that you have a black hole, something that big, you know, and you try to look around it, and you go with the arms around it, and you go from this side. It's like nothing is really, really special. You can go around it, you know, and then you want to say, wait a minute, what is going to happen if I put my hand? So it shouldn't be a black hole. I can take even, you know, a neutron star or something very compact, which deforms a lot of the space. But let's take black hole, for example. And then what is going to happen if I put my hand inside the black hole? You'd expect that the hand is going to come out on the other hand. But the black hole is more or less like the magician thing. You know, you put your hand inside the black hole and it doesn't go outside. You don't see it coming out, and you feel that you are inside the black hole. You say, well, wait a minute, I feel that I'm inside. I really put it along, but I don't see it coming out. You see, so you can put a stick, like Tom and Jerry, you know, you put the stick in the black hole, it's 2 meters, it enters, you see that it enters, you know that it enters the black hole, but you don't see it coming out. Because the black hole itself has a lot of space inside.
So what it's really doing is as it's coming in, there's the decline where you have all that space that it would have to go down, and who knows how deep that is before you would come back up and out the other side.
Exactly, yeah. But remember,
and that's probably an infinite space.
This is an analogy which we are using.
Yeah.
Because when you go with the hand in the black hole, it's not that you go down somewhere, you know, your hand is still in that direction. But in that direction, there is so much space that it can accommodate your hand and 2 meters thick, and you know, we can put 1 kilometer. So that's why actually it's very interesting with black hole, and nobody can calculate precisely what is the distance from the margin to the center.
Right.
So if you take this black hole, and it's only like 20 centimeter diameter, and you ask yourself, okay, what is the distance from the margin, from the horizon to the center, to the singularity? If I put like 1 kilometer stick, will I reach the singularity? No, you are not going to reach. What if I put, for example, you know, 1 million kilometers? So I take meters and I put 1 million kilometers. If I travel 1 million kilometers, will I reach the singularity? No, you're not going to reach the singularity. And there are some people that may say that it can be even 1 light year to go to the singularity. They are not able to calculate because, of course, it's very, very difficult, but certainly there is a lot of space. Okay. And actually, the story is sad, which is Schwarzschild, because he was actually fighting on the front, on the Russian front in the first World War, and he calculated the equation within 3 months. He sent the letters to Einstein, and I think he had an exchange of letters with Einstein 2 or 3 times. And actually, after like 5 months or 6 months, he died. He died in the First World War. So yeah, that's a sad story, but okay, his equation survived.
The legacy.
The legacy survives. Yeah. Yeah. The second thing which we know about black holes is that they bend light around, and this is also some of the nice photos around, and it was supposed to be a simulation, but okay, now this is a PDF. And what you see here, you see the black hole, and you see some strange stuff around. And I say, well, what is that strange stuff? Well, the strange stuff are actually images behind the black hole, which are deformed because the edge of the black hole, let's say the region around the horizon, behaves like a lens, and then it bends the light. And that's why what you see here is basically, for example, the black stuff here is actually some black part which is behind the black hole. And that's why it comes here. And this is a very good point to tell you something about the properties, the physical properties of black holes, because we are here and doing a bit of physics. You know, this is not very advanced physics. This is like the physics, you know, for in the kitchen, let's say. Or
hey, I enjoy it.
Exactly, yeah. So you know what you should do next time when you try to cook? Usually you may listen to music, you know.
Kitchen
try to listen to a podcast about black holes or something, you know.
Yeah, actually, I do listen to that kind of stuff.
Yeah, it brings you to a different world. And actually, I think kitchen is like cooking is like a therapy. So this is also kind of therapy when we talk about black holes. Okay, so some physical properties. First of all, let me no, I'm not going to switch to mine. So you have to look at me here. The point is that when you come closer and closer to the black hole, you are going to feel the tidal forces. And actually, I don't know if I talked yesterday about, no, now I have to talk here about the tidal forces. So I tell you later about that. Okay, we are talking here about the bending of the light. Now, bending of the light, we also saw in the previous episode when we discussed about Edison, so the previous lecture. And we saw that when the light travels in a space without matter, light travels in a straight line. That's what we all know. The laser rays are all straight in an empty space. By the way, in an empty space, when there is matter around, stuff things starts to change. But when there is mass, the mass deforms the space, and then the light cannot travel anymore on straight paths because there are no straight paths. So if you look here on the left side, this is a picture which I have from my physics book, so narrative physics or Physica Povestită in Romanian. And what you see here, you see the space, how it is deformed around the black hole, and we discussed about that. So this is the image of the space in the equatorial plane of the black hole. So if you want to go from one side to another to the black hole, as you describe, Heather, with your hand, you put your hand and a hand goes, and there is a lot of space, because actually the space is deformed, and you go like this and then go up if you go up. But if you go up like this. Now what's happened with the light? You see the light number one, you see the ray is curved because there are no straight lines, and the light, the line here is curved. So it's like you have a bowl, you know, and you are in the kitchen, by the way, and you have the sink, and you saw that the water, you know, travels to the sink, or the sinks, if you put a bowl again, travels to the sink. So the black hole is like a sink, and then the light, you know, is bent. But the interesting part is that the second light, you see, the point number 2, the light is bent, and then it goes inside the black hole. So the light number 2 is never going to escape. They enter into the black hole. And there is a region here where if you put a light, the light is going to travel always, you know, in the center, a light around the black hole. So that's what you see on the right-hand side. You see again the rays, and you see here a point here where it forms a sphere. So if you follow this ray, you see this is more or less like a sphere, and this is called the photon sphere. So in other words, you are not yet in the black hole, but the light itself goes around, like in a merry-go-round, in the black hole. And that's funny. Why is it funny? Because if you are at that distance, so you didn't enter the black hole, because the black hole would be like the radius, Schwarzschild radius, but you are 1.5 radius, Schwarzschild radius. And if you look on the right-hand side, you are going to see actually your left ear, because the light from the left ear travel around the black hole, and it comes from the right part. You know, so you don't need a mirror, Heather.
So it's kind of stretching. No need for a mirror. It's stretching around and then coming back to
exactly
where it started.
You remember, and probably you know, if you have a mirror, if you try to find yourself what is here on the back of your head, it's also very difficult with a single mirror. You turn your head, you still don't see your back. But
right.
if you are on the photon sphere, you know, you look just in front of you, then you are going to see the back of your head. But the lights from the back of your head travel around the black hole, and you are going to see.
And then you're like, oh, that's what I look like.
Exactly. I never saw me like that. I was a
That's
person.
funny. That's a good analogy.
Yeah, and that's actually the photon sphere. Then we have the horizon. The horizon is actually the point of no return. And remember, in the center of the black hole, we have the singularity. And maybe I'm going to talk later about the singularity, I hope, to tell you. Otherwise, remember me to tell you what is in the singularity, because everybody is interested. What is in the singularity?
What is in that singularity?
Yeah. But let's keep it a little bit like under tension. you know, like wait for the end of the movie, and talk a little bit about these tidal effects. Because the point is, if you're close to go and try to be closer and closer to a black hole, you are going to feel some forces which stretches your body. Indeed, indeed. And these forces for a stellar black hole, what we discussed up to now, are going to kill you when you are at about 20,000 kilometers. So if you come close to 20,000 kilometers, then you are not going to survive, because they stretch you so much that you cannot stand that force. And this particular case is 15G. Now, what are these tidal forces? The tidal forces are differences. So let me switch to me again. The tidal forces are differences in the force of gravity. So remember, so let's suppose that here down, we have the black hole, and we enter with the foot. You know, in principle, both the foot and the head are drawn by the force of gravity, so you fall into the black hole. But there is a difference, because your foot is closer to the black hole, it's going to be pulled with a larger force than with the head. So that's why you are going to feel stretched. But because you are at the same time falling, one moment, I let you, because you are at the same time falling, you're not going to feel that you are stretched by the foot, but also by the head. So you feel like somebody is also stretching your head. Say, Heather, what do you want?
Yeah, you would think that with that amount of force, at the same time you would be falling. At what?
Yes.
Wonder at what moment, at what point, the bottom half of you, I guess, would feel like it's stretching more, and it would feel like, I guess it would sort of like rip you apart.
Yeah.
And then where your upper part of your body is then being stretched. So you're never going to find out what's in the center of a.
So basically, for the stellar black hole, because the stellar black hole are smaller, so remember, radius of 10 kilometers, you know, that effect is strong even when you are 20,000 kilometers away. When you are 20,000 kilometers away, you feel a force equivalent to 15G. You know, the normal force which we feel is G. And you saw these astronauts, when they go outside, they feel a strong acceleration force. But Kip Thorne, because I have his book here, and I took the number from his book, I said it's 15G. So in other words, your feet is going to feel a force which is like 15 times larger than the usual gravity, and you cannot stand that.
You wouldn't be able to stand it. It would happen so fast, that kind of force plus being pulled, it would just be instant.
Yeah, it would be the end. But this is for a stellar black hole. We are going to see that in the universe we also have giant black holes, which they live at the center of galaxy, and we are going to be able to survive for that black holes. But we come to that as well. In a moment. So it doesn't look so grim up to now. But this tidal force, the thing I wanted to say is that this tidal force which we see, it has the name from the tidal force which Moon exerts on the Earth. Because that's happening. The Moon exerts a force on the Earth, and we have water on the Earth, and we have oceans. What is going to happen with the water which is close to the Moon? Well, the water is going to be lifted up. So that's why we have this, how is it called in English? Again, this effect of tidal effect, when you have the water going up and water going down, water going up, water going down.
Oh, like evaporation?
No, like the ebb. I forgot. Flux and reflux. We call it in Romanian flux and reflux. Okay.
Okay.
So when you go at the sea, and then the level of water increases, at a certain.
Oh, that's the high tide and low tide.
Exactly. High tide and low tide, and you have here high tide because
the ebb and flow
pulls the water. Ebb and flow, yeah. And then what is interesting here, that's why I put the picture. you would expect that on the other side of the Earth, then there would be the opposite, which is not the case. You see, the water is also high on the other side, which is kind of strange, because here the force should be smaller, and the force is smaller, but the water is here high because of the centrifugal force. And this is basically what I like, the comparison between the two, is that the Earth as well as the astronauts, they kind of free falling or something like this, and the tides are at both ends. So in other words, even though the astronaut is falling, he's feeling that he's pushing harder by the foot in one direction, by the head in the other direction, even though he's actually pushed stronger only by the foot. But it's the fact that he's falling free. And it's the same with the Earth. Okay, a little bit more complex. Let me see what I wanted to do here. Okay. I said, well, let's look at this picture here. Very nice picture from Interstellar, I think. And you see the top part. And what we see here, this is the accretion disk, which is around the black hole, because the black hole eats some material after, the black hole is formed, and the material goes into the black hole, but before going into the black hole, it forms an accretion disk. So if we look here, for example, at this picture, some material from the stars, goes into the black hole, but before falling into the black hole, starts to go around the black hole. And it's also because most of the black hole rotate themselves. And that's normal, because the stars from which they formed rotate. Is like with the neutron stars. So then the black holes rotate, and it's very interesting. Once they rotate, they also rotate the space around them. And because they rotate the space, they again put the matter in motion around the black hole. So they form an accretion disk with matter. And this is what we see here on the left side. This is the accretion disk around the black hole. But the point is, what is this here on the top? Because this is certainly not the accretion disk. And this is something they didn't explain in the Interstellar movie. So I thought, okay, since this is physics, let me explain this. And I had here a small thing from my YouTube channel, and I wanted to show it to you, but this is PDF, is not going to work. So if you want a better explanation and a longer explanation, just go on my YouTube channel. But the idea is the following. This is the image, and what you see here, you see the black hole in the center, and what you see here is the accretion disk. So this horizontal part is really the accretion disk. And then the matter actually continues to go back, on the back of the black hole and go around. In other words, the accretion disk is like what I do here with the apple. I have the apple is like the black hole, and the accretion disk is just a normal accretion disk. It's just a disk in the horizontal plane, nothing special. And then why do we have here this top part? Well, actually, this is the image of the back of the accretion disk. The back of the accretion disk, because, and let me explain here, if this is the accretion disk, and then I look at the accretion disk. So, for example, you look at the accretion disk, you see this part from the front. There is a part on the back, but remember that light bends around the black hole. So the light is going to go like this and then goes towards you. You see, and go like this and go towards you. So you are going to see here on the top an image of the back, and on the bottom you also going to see an image of the back accretion disk. So if I go back here, and I say...
it looks almost three-dimensional.
Exactly, it looks almost three-dimensional, but this is actually the back part of the accretion disk, and it's also the back part, but the bottom part. I saw that there is maybe a question here.
Let's look here.
Tides.
Oh, tides. Yes.
Yeah, exactly. Yeah.
The ebb and flow.
Exactly, yeah. So then let's go for it. Okay, so we have 20 minutes more. I think I will make it in time. 20 minutes is okay. One moment. Okay, and this is about singularity.
Okay.
Because this is the black hole. let me switch to me again a little bit, because this is the black hole, and the most important thing from this lecture is to remember a black hole is empty space with a singularity in the beginning. So what is it going to happen if, let's say, suppose that you survive and so on and so forth, and you go into the singularity? First of all, you are going to pass the horizon. Even though for the stellar black hole is difficult, for the other black holes are more easy, we're going to see. But the point is that you pass the horizon, and then you are going to go to the singularity. Remember what I told you, there is a lot of space until the singularity. So even though the black hole is like 20 centimeters, you may have to travel, you know, let's say 1 light year or millions of kilometers or something like that. But we discussed about, and maybe I show the screen, we discussed about the fact that we have the tidal force once you approach the singularity, you know. And once you enter, once you approach the black hole, once you enter the black hole, the tidal force is even larger and larger and larger and larger. So then if you enter the black hole, this is going to what is going to happen. You see here a guy from the bottom left entering a singularity with feet first, entering the black hole and approaching the singularity. And I borrowed this picture from the book Black Holes, which I showed it to you, from Kip Thorne. And I copied because I think, okay, Kip Thorne, he got the Nobel Prize, he made, you know, Interstellar movie. Is the best one.
We'll post that. We'll share that book. That's a good.
Yeah, it's good to know, because this is the best book on black holes, in my opinion. And this is the best picture. So when you approach the singularity, you see the guy is stretched and stretched even more. And you see here, the foot basically touches the singularity. But at the moment when maybe the foot is going to touch the singularity, the guy here, you know, the guy here, maybe thousands of kilometers or maybe millions of kilometers long. Not you know 100 meters or something like this. It's going to be so much stress that we are talking here. I think of millions of maybe 1 light year or something like this. It's really stretched a lot. And on the other hand, it's going to be squeezed in the other direction, because it's approaching the singularity, and the closer the singularity you are, the more squeezed you become. You see the 2 arrows here. And then the foots are maybe going to be squeezed not at the dimension of the atom. So it's like even smaller than the atom. So you can imagine to be stretched on the distances of billions of kilometers and to be squeezed in the direction on a dimension which is like the atom. It's unimaginable.
Basically, you're becoming like a line.
You're becoming like a line.
Yeah.
Exactly. It's a very,
an
very
infinite
nice
line.
In
Light
English,
years.
they call it sometimes spaghettification. But I think what you say, line, is even better. Because if you look at the spaghetti, they are still large, you know?
Yeah.
But a line is so thin, it's like very, very thin, and that's what you become. And then, what is going to happen when you touch the singularity? That's the big question.
So say we survive all of that.
Yeah, survive, and then you just go to the singularity. Now, the first thing to tell you is that in order to reach the singularity, even if you have a distance of let's say 1 light year, if the stellar black hole is a normal black hole, you reach the singularity very quick, in a matter of minutes. And it's very, very strange. So even though you travel a distance which is like 1 light year, so normally if you go with the speed of light, it would take you 1 year. No, you reach for yourself, and let me maybe show it to me. If for yourself, you reach the singularity in a matter of minutes. And why is that? Because your body approaching the singularity reaches speeds close to the speed of light. And we know from Einstein's theory that your internal clocks starts to almost freeze, you know? So your atoms barely don't move and your electrons barely don't move on the orbit. So it's like you're freezing. And then when you approach the singularity, you may think that you talk normally. So you say, well, I have 4 minutes until singularity. But actually what you are doing is like, I have 4 minutes. And you're talking like 1 year long.
Yeah.
You know, because you're
Well,
talking.
with the time-space distortion, that seems, you know, that's
Yeah.
what would happen. It would be so long, yet for maybe in us, if we got to that point, it would seem like it was like a split second.
Exactly, exactly.
Mhm.
And let's also
Yeah.
remember, so in other words, you reach the singularity.
So
But
we
the
got
point is, what are you going to see at the singularity? You know, and that's the when I try to read the Kip Thorne and all the other books, you can hear me, yes? Yes.
yeah,
Uh,
yeah.
so and I read this book, and because I also found myself when I calculated the equations, because when I wrote my also book, my Physica Povestita, or the story of
Mm-hmm.
physics, I calculated the equations, and I was surprised because the equation told me that for you, the time will end at the center of black hole. And I was so surprised. I mean, what does it mean for the time to end at the black hole? But this is what you do. You take the equation and you say, and you get like t minus 4 equals 0. So
I was
that
gonna
means that
say,
the
so is
t
it zero?
for
That's like the
4
void.
minutes,
Mm-hmm.
your time ends. There is no more time to you. And it's so
Oh.
strange. And then I read the black hole, and he says the same actually. When you reach the singularity, time ends for you, and space does not exist. Like, what is, it's like, you know, at the beginning of the universe, when there is no space and no time. So the singularity is like a small mirror of what it was before the Big Bang. And then, of course, we have to formulate a little bit more precisely that, and then get out of the poetry. But at the end of the day, what we physicists say, well, actually, we don't know what is it at the singularity. Because in order to understand what it is of the singularity, you have to merge Einstein equations and Einstein equations and quantum mechanics. And nobody did that. And because of that, we just don't know what is going to be at the singularity. But reading Kip Thorne and saying, well, the time ends, I have to say, well, actually, I need it's something like this. The time as we know it ends.
As we know it, yeah.
As we know it.
But I like staying in the poetry of it all as well.
I also
It
like
kind of
the
keeps our
poetry.
imagination going.
Exactly, yeah. And I like this comparison with the
Sort
Big
of,
Bang. Before the Big Bang, it's like when there was not, when something is something you cannot imagine. But okay, I mean, the physicists are going to solve the quantum gravity equations.
we can
So
imagine feeling that kind of space of what it would be like. So.
exactly. But just to be sure on the safe side, I have to add that
Oh,
once
okay.
once the physicists are going to solve the quantum gravity
Yes.
equations, all the poetry is going to disappear.
Oh no.
And then we are going to have equation with
No, that's an important part of it too. It's
yeah, and then we are going
the
to have
language and the
equation.
mathematics and the equations, but some might argue that that's part of the poetry. I think I would anyway, but I digress.
I agree with you. If you say it is part of the poetry, okay. But I would say to be on the safe side, the poetry disappears, and then the equations are going to tell us what happens inside the.
Okay.
Okay, now for the last part of the talk, which I don't think I'm going to make it in 10 minutes, because I wanted to tell you about the evaporation of the black holes and the giant black holes, which are in the center. Let me see. Supermassive black holes, they are called. But again, so I'm going to skip a little bit this, even though I had here some formulas for the guys. So I'm going to tell you just very, very, very quickly for the guys who want to know a little bit about the physics of the Hawking radiation, which you can calculate yourself, which I calculate also in Physica Povestita. And you can do with some small formulas here. The point is that you have virtual particles on the horizon, and once you have virtual particles, you are going to have here pairs of particles and antiparticles, and one of the pair is going to go into the black hole, and the other one is going to go away. And how do you calculate the Hawking radiation? What you need in order for this pair to become real, you have to give it energy. And how you give it energy? You give it via the gravitation. So what you have here is a pair and the pair has more or less the distance, which is like the Compton wavelength, which I mentioned last time. And then because of the tidal forces, which we remember that we discussed, one particle is going to feel a larger tidal force is going to go into the black hole, and the other one, a lesser force, is going to go the other side. And you can calculate the energy which the pair gets from the gravitational field. And that energy gives you what is the energy of the virtual particle, because if the virtual pair, because if the energy is enough, the virtual pair is going to become a real pair. And this is how you do. So basically you calculate here the energy and you say, well, the energy should be equal with mc square. Actually, I think here more or less it should be a 2, but this is a rough calculation. So you have to give energy to this particle to become real, and that energy actually is equal with more or less equal with the thermal energy, and from this you get the temperature. So you can yourself calculate the temperature of the Hawking radiation. This is the only thing I wanted to tell. And the last part is about the supermassive black holes, because now we discussed the black holes which appear after the explosion of the supernovae. But these black holes are called stellar black holes because they have a mass of few suns. But we know that in the universe there exist supermassive black holes. We have masses of millions of suns, but literally millions of suns. And they are larger. Because they have millions of suns, the horizon here of the black hole is on the size of the, let's say, a little bit smaller than the solar system. So this is a very large black hole, but the good part is because the black holes are so large, the tidal forces are so small, so in principle, we humans can travel through the horizon of the black hole and enter the black hole. Of course, if we enter the black hole, what we are going to see there inside the black hole is empty space. And for that matter, the supermassive black holes look like the normal black holes. It's just that they have a much more space inside. So even though the size of the black hole here may be like the solar system, when you try to travel to the center of the black hole, you may travel literally thousands of light years. There's so much space there. As I told you, nobody really can calculate that. And the supermassive black holes, they also have other things, like they certainly rotate a lot and they create big accretion disk around. And we know, for example, that there is a supermassive black holes inside our galaxy. So I go very fast right now. How we know that? These are some stars whose orbits are drawn by looking with the telescope in the center of our galaxy, and they draw here let's say the motion of the stars, and they calculate
the photograph.
Yeah, from this they can calculate that here in the center there should be a supermassive black hole. So in our galaxy there is a supermassive black hole. This is a nice picture which shows the main element of the supermassive black holes. Again, tidal forces are small. So in other words, you can jump into the black hole, you can cross the horizon. But by the way, people outside will never going to see you crossing the horizon because the light cannot escape. So you enter the black hole, you have a good time inside the black hole, even though you never return, but you have a good time in the black hole. But the light from there cannot not escape the black hole. So nobody's going to see you inside the black hole. The people are going to see you more or less sitting on the black hole here because the light goes very, very hard outside.
They'll see us sort of bent around the black hole.
And then you see here the accretion disk, which is made of the star, which usually the black hole eat around. And so the tidal forces sometimes destroy the stars, so they have like dust here, and then forms a jet. Forms accretion disk, and then this accretion disk. So the matter here is ejected at the north of the pole of the black hole, and this is what we call a jet. And this is actually a picture from my book where I said that look, black hole exists, and I made some calculation from the galaxy M87, and that was in the year 2014 when the book appeared. And of course, everything was new, and I repeated what others said in the articles, but it was a kind of very good evidence, but not certain, that at the center of this galaxy, there is a black hole. And on the back, on the right-hand side, you see the first ever picture of the black hole. So this is a real picture, and it's the only picture we have of a black hole. So the thing which you see in the center is really, in the center, is really, really a black hole. And what you see here with light is really, really accretion disk. And because it's the first picture, of course, it's not the nicest picture, but I found it a little bit funny that actually they measured the same galaxy, M87. So when decided to measure the first black hole, they measured the same galaxy, because they also said, well, actually, the evidence is so strong here that there is a black hole. So they and I say, look, I had that in my book. So, okay, it's good. That means that it was a good choice.
Wonderful. Hey, I had a quick question from somebody. They were asking about your books again. If you have them, would you mind showing them, and we'll make sure they get posted, the books that you were, your book and the other book?
Okay, so I'm going to show it immediately. So just the last thing I wanted to tell you about the quasars. And now that I don't have the video, it's even faster. So the quasars are active galaxies which have at the center a very, very strong black hole. And because of that, they eject a lot of material. And what you see here on the right-hand side is a real picture of the jet coming from a quasar, from an active nuclei galaxy. Actually, I don't know if this is a quasar. Oh, no, this is not. I was wrong. This is wrong. This is M87. So it's the same galaxy, actually, where the black hole was measured. So this is not a quasar, because M87, I think, is not that active to be called a quasar. But M87 has also a jet. So what you see here, this is really, really a jet of matter escaping. But quasars have very, very strong jets. And then those jets have magnetic fields, and the magnetic fields have charges, and the charges produce radio waves. Okay, and I think I will not talk about the portal universes and so on and so forth.
We'll save that for another conference for sure. We could talk about so much about the quasar stars are a whole nother topic. Yeah. Would you show your books for us? Okay.
So this is the big book,
yes.
Physica Povestita. And then I talked about black hole, the best book on black holes, Skip Thor. And then let me see, the other book is with many illustrations. And this is more like for kids of age 10, 12, or something like this, because it has this these very, very nice drawings inside, and with the text. So if there is some time, but I don't know if there is time, because this is precisely the time when we have to stop.
Yeah, well, we like the drawings too. They're pretty amazing. We've seen that one. And I just want to say thank you so much. I think what all this has done, at least for me, and everything about space always gets me super excited, but it sparked a new curiosity for neutron stars, for black holes, for white dwarfs, how they're formed, what we're learning about them, and what we hope to learn. So hopefully our listeners are on Facebook and all our social media platforms, as well as here, will get curious and start doing their own research and get excited about all the space research that's going on. That's really amazing. I hope we've come a long way from that first black hole photograph.
Yeah. Yeah, it's true.
But I just want to say thank you. Let's see.
You're welcome.
I see one. Somebody says, fantastic presentation. Thank you so much. All the planets and stars would certainly die after trillions and trillions of years, and only black holes will thrive within the universe. If any future generations would exist during these times, could they harvest energy out of the black holes, theoretically speaking?
The answer
and I
is
actually
yes.
had a similar question about energy. If you want to touch on that really quick for us.
The answer is yes, and there is a big yes. I mean, I'm personally surprised how many physicists say that it's realistically possible to extract energy. There is actually a mathematician called Roger Penrose, which I think he came for the first time with a tool around the black hole to harvest energy. And also Kip Thorne in his book has also kind of installation or device which you can build around the black hole to harvest energy. And the basic idea is the following. Most of the black holes, they rotate around and they take the space with them. And the fact that they take the space with them, that means you can construct a dynamo. Remember, when you have a bicycle, you know, for the modern bicycle, you don't need batteries. For the modern bicycles, you can have a dynamo, and because the bicycle wheel rotates, you can take that energy and use the dynamo and have electricity. It's the same here. You have here a free wheel of the bicycle, and the wheel of the bicycle is the space which is moving around because of the black hole. And people calculated, if you put there some magnets, you know, and then the space is going to take the magnets around, and the magnetic field is going to be variable, and every variable magnetic fields create electric field, so it induces currents, and then you put some coils here, and in that coils you're going to have electric fields, then you have here an electrical generator. And they calculated that you can get 20% of the energy of the black hole. So it's not only very realistic, but I'm surprised that physicists believe in such science fiction things.
Well, often science fiction becomes that science fact. So
exactly, yeah.
We have to start with with these sort of seedlings of ideas and thoughts. You know, that's where it begins. Yeah. Wonderful, good question. All right, I'm going to wish everyone a super evening. Buonasera to you. Yeah. Thank you so much. We look forward to connecting with you in the future as well. And thank you for sharing all your wisdom with us today. We really appreciate it. So to all our listeners, we hope to see you again real soon.
Okay. Have a nice evening. See you then.
Buona.
No, l'arrivederci.